Chapter 25 is our Gauss's law unit. Now, Gauss's law is going to give us a specific technique to use to calculate the electric field out of very specific charge distributions, and we're going to see more about that in detail as we go through this chapter. But to start to understand Gauss's law, we need to first understand this concept of flux, and specifically for us, electric flux. So as it says here, we are going to focus on this first page of notes in trying to get a better feel, or a feel, for what is meant by electric flux. Now, we're going to start with a definition. So we can see here that we have our definition 3 = sign of electric flux. Flux is given in general, whether it's electric flux or magnetic flux, or flux as a concept is given by the Greek letter phi, capital Phi. For us, it's a lower script E here for electric field, and we can see, as it says here in our definition, that the flux value through an area A, so our area A, we will always be interested in what area are we talking about the flux going through. So my example over here that I'm coloring in shows that the area A is this pinky purple color, just this rectangular sheet of paper. Now, if we were interested in the electric field that was passing through this sheet of paper, we would not be interested in the electric field that passes along the paper. So this E parallel, as it says here, makes no flux. So please make sure you get all these annotations completely into your notes, because it is only the E perpendicular component of an electric field that passes through, and in general, you can have both of these components as part of an electric field, but it is only the E perpendicular that will contribute to our calculation for flux. So flux is a product quantity based on the electric field that passes perpendicularly through the area times the area itself. So you can have a large electric flux value for one of two reasons, or a combination of the two, meaning that you have a large value for the electric field itself, perpendicular, passing through the area, or you have a large area. Now, you'll notice this n hat vector that we have in here. So this is a n hat normal, so the little n is for normal, mathematically normal, 90 degrees to the surface area. And that, as it turns out, let me zoom out here a little bit, is going to give us a very important definition for area as a vector. So this is a new concept to us. So we are introducing area now not just as a scalar meter squared, like base times height, but we are giving it direction. So the mathematicians have determined that by defining this, right? So they've just determined it's useful to say that the area will have a direction to it, n hat, and that it's going to be perpendicular to that surface area. So that's all that is on this first page of notes. It's really just getting us used to this concept of a product quantity, that the electric field that resides within the plane, so any electric field that rides along an area will not contribute at all to the flux value that we're going to say passes through that area. E perpendicular is the only portion of the electric field that gives us contribution to our flux calculation. We show here that our units for flux are going to be given by electric field in newtons per coulomb, area in meters squared, so newtons per coulomb times meters squared. And our final recap is to just make sure that you understand, and if you have any questions, please make sure you ask. As to this area vector, it is defined to be a vector A that has the magnitude of the area, and we give it direction, n hat, because it turns out to be useful, and we'll see more about the usefulness of this on our next page of notes.